Hello and welcome. My name is Artem Polevyany. I am a senior lecturer at the School of Computing and Information Systems at the University of Melbourne. In this video, I will present our work authored with Andreas Scholti, Matthias Weidlich, Claudio Di Ciccio, and Jan Mendling. This work proposes new precision and recall measures to compare executions and designs of systems. So let's get started. Conformance checking is an area in process mining that studies the problem of comparing process traces described by a process model of a system and an event log of recorded historical process executions. A solution to this problem allows assessing the level of agreement between the process design and the corresponding real-world executions of the process. These insights can drive process redesign and improvement initiatives. Two standard measures for assessing such a degree of agreement are precision and recall. While precision aims to assess whether the model allows behavior not in the log, with less extra behavior leading to better precision scores, recall measures how well the model represents the traces from the log. For the model and log shown on this slide, we expect precision and recall to be high. Indeed, together with all the 5 traces from the log, the model describes only one additional trace. The standard way for measuring precision and recall between model and log can be understood by analogy with information retrieval. An event log represents the relevant traces we want to see in the model, and in process mining, given a log, we feed it into a process discovery algorithm that retrieves a model based on the input log traces and some assumptions about the actual system represented by the log. And these assumptions are inherent to the design of the algorithm. The model and log can then be interpreted as collections of retrieved and relevant traces. And then precision can be measured as a fraction of retrieved model traces that are also log traces, while recall as a fraction of the relevant log traces that are also model traces. Considering the example model and log, precision is equal to 5 divided by 6, while recall is equal to 5 divided by 5, or 1, denoted perfect recall. And as I said, the model describes only one extra trace compared to traces in the log, and this trace is ACGHDFI. One can come up with several candidate models that aim to describe a given log, and then precision and recall measures can help to prioritize candidate models. For example, in the top left, the single trace model describes only one trace that is also present in the log. Hence, this model has perfect precision. However, it has a low recall, as the model does not describe the other 4 log traces. Conversely, the Plover model in the bottom left has perfect recall. Indeed, it can describe all possible traces across the corresponding alphabet. However, the precision of this model is low. The 2 models on the right have perfect recall. Each of them describes all the traces we see in the log. But deciding which of the 2 models is better in terms of precision is not easy. Both models describe traces outside of the log, but which should be more precise is not immediately apparent. And one reason why it is challenging to rank those models in terms of precision is that they describe infinite collections of traces. For instance, model 2 allows arbitrary interleaving of an arbitrary number of occurrences of actions G and H, and unless we find a way to compare infinite sets, any 2 models that describe infinite sets of traces will be incomparable. Here we need to decide whether precision should be 0 or some other value, and any such decision we take will inevitably have consequences of not being able to compare some models. To overcome this issue of infinite sets, instead of measuring their cardinality, we propose to estimate it using the notion of topological entropy. The definition of the topological entropy of set of traces is given on this slide. And to explain it a bit further, B here is an automaton that describes the traces, and B hat is its transformed short circuit version. And refer to our journal article for the details on this particular transformation. Cn is a set of all traces of length n that B hat accepts, and still it is not immediately clear how to compute that limit superior when n approaches infinity, etc. And to that end, we use a well-established theory that tells that entropy is equal to the Perron-Frobenius eigenvalue of the adjacency matrix of the automaton B hat, where Perron-Frobenius eigenvalue is simply a largest eigenvalue of the matrix. Finally, we propose replacing cardinality measurements with entropy measurements to obtain entropy-based precision and recall. Recently, Nick Tax and his collaborators observed that existing precision measures do not fulfill 5 intuitively desired properties. So crosses in the table mean that the corresponding properties were demonstrated to not hold for the corresponding precision measures. These properties tell that precision should be deterministic, should be independent of a particular way the model is drawn, but depend only on the trace it describes, that the flower model should have the worst precision, and that the model that describes fewer extra traces outside of the log is more precise. See, for example, properties A2 and A5. We showed that our entropy-based precision satisfies all 5 properties. In addition, we showed that our measure satisfies stricter versions of the properties that use strict inequalities. So even if collections of traces described by the logs and models differ by a single trace, our measures will be able to detect that. Even more recently, Searing and collaborators demonstrated that our entropy-based measures satisfy the revised and extended repertoire of properties for the corresponding classes of measurements. And for more information, I again refer you to that paper. As of today, our precision and recall measures are the only measures that satisfy all the above stated properties, and this also leads to different conclusions about the quality of the models than conclusions due to some other measures. And the dataset shown on this slide comprises 1 event log and 9 candidate models for describing this log. This table compares rankings of the 9 models from the dataset as per their precision scores with respect to the sample log. 9 precision measures were used in this comparison, and rank 9 in the table stands for the absolutely best model in terms of precision, while rank 1 says that the model is the lowest in terms of precision. The bad news is that no 2 rankings are the same. The somewhat positive news is that the ranking derived by our measure shown in the column EB in the table is the ranking that adheres to all the desired properties. So we know how theoretically the ranking should look like. But what about those 2 models I showed to you in the beginning? So which one is better in terms of precision? Some of you may already notice that those 2 models come from the data set. So model 2 is the H and G in loops model, and model 3 is a D in a loop model. Also, the only log in the dataset is our example log. And according to the entropy-based precision, model 3 is more precise with respect to this log. Note that model 2 describes more traces of any given length, as G and H actions can interleave, leading to more trace variance that model 3 can possibly produce. This our line of research on the entropy-based conformance measures turned out to be quite fruitful. Since the publication of our article, we have published papers on tool support and extensions of the measures to support partially matching processes and stochastic processes. So plenty of reading for you if you want to learn more about our techniques. So to conclude, our measures satisfy all the currently recommended properties. The tool for computing the measures is called Entropy and is publicly available. We work on improving the performance, but the measures are already very fast for the process models discovered by commercial process mining tools. Much has been done, but also much can still be done. And as immediate future work, we identify the extension of the measures to handle the infinite state systems. Yes, we can handle models that describe infinite collections of traces, but currently we cannot handle models that describe an infinite number of states. And note that those models cannot be captured as finite automata, but still can be used to describe some useful real-world systems. Finally, all the properties I mentioned were proposed by academics, and I believe that further validation of these properties by their stakeholders is desirable. And with that, I want to thank you for your attention. Bye-bye.